Hello. So today we're going to be talking about tracing in environments that you don't control, where customers are running your software. So just a quick agenda. I'll introduce us, introduce the topics, talk about what our API and UX is like for the tracing system we built, a little bit of the analysis you can perform, and we'll do a quick demo and hopefully have time for plenty of questions at the end. So this is my colleague Alan Carbanda. My name's AJ Ortega. We're both engineers on the cloud data transfer team at Google. We run software that copies files between cloud blob providers as well as copies files up and down from on-prem and cloud VMs to cloud storage providers. So just to give some background on the problem real quick, we needed to solve tracing because we're constantly getting customer queries, et cetera, for why is my data transfer slow, and we don't have a great ability to look in at metrics and other information about the computers that our customers are running software on. So the machines or VMs that our customers are running data transfers on aren't accessible to us at all. And we ship a single binary in a single container. There's a lot of reasons why we're stuck with a single binary, so we can't do something like add a sidecar or agent. We have to be able to trace in process. And we need to both generate the traces, move them somewhere we can analyze them, and provide an analysis workflow that our developers can use without having to spend a ton of time learning like a whole new operational system. So how do we bring that all together? There's many existing solutions for tracing. We evaluated a lot of them before we looked at building our own thing. Cloud tracing, for example, is great at looking at many microservices or latency of a particular request. There's other cloud tracing services that provide powerful distributed tracing, as well as like system calls. They do a really great job at kind of tracing per request, per invocation, or otherwise in scoped in traces, but we needed the ability to trace across a whole data transfer that could take hours or days in some cases if someone's uploading multiple petabytes from on-prem up to, say, Google Cloud Storage. So to start, I'm going to go into a little bit of what our API looks like. We have a tracing system that looks very similar to a lot of what you've seen in the last couple of days. We trace the beginning and end of methods. We have a facility for adding general metadata. So that could be error types, maybe a count of, if say you're listing a number of objects or a number of files in a folder, or general strings that developers might want to know to provide context for why a particular method may be performing a particular way. Besides metadata on trace events, we have the ability to attach metadata to a Go context. This will make a little more sense when I get into a code example. But this metadata flows down and provides basically a span functionality. So this is really useful if you want to know, say, I'm transferring a particular file with a particular name. At the top level handler that's copying that file, you can attach that file name, and then as you go down into low level functions and syscalls and are tracing them, you can know the context that this syscall is being called to transfer this particular file and eventually build together a DAG, essentially, of what the execution was looking like in your program. So what does this look like? Here's a really isolated sample of our library. So whenever you want to track a method, you use our start. It's actually event logger.start, but this code sample was written in the same package, so it's missing the prefix. You have to name your event. There's no real requirement or structure on the name. Our code is small enough that developers can kind of guarantee that each string is unique. We tend to suggest that the engineers use a qualified package name for the record, but it can really be any string, and it could match something else, although that would really confuse you during analysis later. After you start an event, you immediately want to defer ending the event. This is a Go keyword that's really useful because even in the face of a panic or stack unwinding, defer always executes. So in functions that are particularly likely to exit unexpectedly, you can still get a performance trace and know when they exited, as well as, if you want to, even attach metadata about the panic or unwinding. You can see there we're setting a key and value of metadata. This can be anything, though. It all gets serialized to JSON and then eventually a string. And then any metadata you're setting gets passed down along in the context to further methods. So in second method here, you see this, to simulate work, we're sleeping for 2 seconds. So going into what this actually looks like when you start analyzing the data. The first event from the first method is on the left. The second event's on the right. These are ends. We add timing information to the ends. So we log a start event and an end event, but in the end event, we always include the duration so that when you're querying, you don't actually have to worry about the start or do any kind of like calculation or analysis. But starts are useful when you're looking at hangs. So you can see this like key value that we added in the function are available under the metadata heading, and spans that were added somewhere in the stack appear in both. So this example span key, example span value could be something like the file name that's being transferred, like I was mentioning before.
Thanks, AJ. So there are three, as AJ discussed, there are three major parts to this. One is generating trace logs, second is shipping trace logs, and the final part is analyzing trace logs. So we have already generated the logs, so now we are going to move to how to ship these logs to cloud. There are two major methods of shipping logs, in-stream and out-of-stream. In-stream basically means you use something like cloud logging to immediately set the emission of the log, while out-of-stream means that you write it to a file and get it uploaded later on. Shipping logs in-stream, we found that the Google Cloud Logging SDK was the best method to do the same. For shipping in-stream, you simply have to say, hey, log.emit, and all the logs are buffered in memory. However, you can go ahead and define restrictions that, hey, I only want 1 million logs to be held in memory, or I want logs worth only 1 GB to be held in memory before they start dropping logs. Instead of dropping, you can also define behaviors that make it blocking or non-blocking and drop. There are pros to this approach. There's no file management involved. The SDK integration is super easy, and the integration with BigQuery is excellent for cloud logging. All you need to do is to create a sink, which would move all the logs that you have shipped to BigQuery for analysis. However, there are some cons. One is this will eat into your memory. And second is, depending on how many objects you're generating, you may run into limitations of the Go language, because Go garbage collection treats all objects the same. So even if it's a short-lived object, it would end up occupying space on the memory, which would need to be garbage collected later. There is a method to ship them out of stream. Basically, what you do is you keep on generating these logs and write them to a file. If you're using a good JSON conversion library like JSON iterator, you would be converting using only the stack memory and not the heap memory. As a result, there's not much garbage collection to be done. The way we do it is we create separate threads to keep analyzing which log files have already been generated, and then we a scanner runs and compresses those files. Then there are separate threads which look for compressed files in a compressed file directory, and they ship them to Google Cloud Storage, GCS, which is a blob storage on Google Cloud. The pros in this approach are it has far less memory utilization, way low garbage generation. You can choose the compression algorithm to optimize speed versus efficiency based on what you prefer. We use the GZ format because that is directly integratable with BigQuery, but you can choose your own custom compression format, or if you have a custom compression algorithm, you can go ahead and use that as well. Again, it's an easy integration with BigQuery, although as a con, it requires some manual pulling in for analysis. And there is a delay in shipping as compared to cloud logging. In cloud logging, your logs are usually available within a minute, but in case of the out-of-stream shipping, you could have to wait up till 5 minutes, which in our use case was completely fine, but you would have to pick the best method for yourself. There's a big question on whether to sample logs or not. In our use case, we wanted all the logs because we wanted to track missing events. We wanted to track events which have been left open and not closed. However, that is something, again, which is completely personal, and you can choose your own sampling rate in case you feel that is more optimal for you. When you track all the traces, you can identify the unclosed events. You can, we'll see an example of that. You can also test statistics in aggregate. You can identify hotspotting and concurrency needs better. And you can start doing pattern analysis, track anomalies, find errors, have a higher chance of finding errors. Now, we have gone through two parts, generating logs and shipping logs. Now let's go to analysis. And for analysis, we realized that BigQuery is the best tool available in the world. And the reason for that is BigQuery is highly optimized for running SQL workloads. You are limited only by your imagination when it comes to what you can query when you have all the data. And BigQuery is extremely fast, extremely optimized, as we'll see in the demo later. Again, to import logs, if you use the cloud logging method, the in-stream method, then you can create a sink and have logs shipped to BigQuery directly. Or if you use the out-of-stream method, the logs go to GCS bucket. You could pull in manually. You could write scripts to periodically pull in logs into tables. And you can directly import GZ files, so which basically means that all your uncompression happens, again, asynchronously, and you don't really have to worry about getting the uncompressing logs before you write them to BigQuery. For queries, BigQuery allows you to create and save project templates, query templates, which basically means that for any service, if you have a certain set of queries that need to be run, you could save them and don't really have to worry about writing queries all the time. In our use case, for example, we have about 10 or 12 queries which we need to debug our service, and we just keep running the same queries, maybe change a parameter or two about the event we are tracking. You can write compounded queries pretty easily. If you're not good at SQL like me, all you need to do is create temp tables and write to them and then run a query on the new temp table, and that is still very, very fast with BigQuery, as we'll see in an example very shortly. You can use this for constant analysis, have this periodically running, for example, integrated with the integration test or something to make sure that if anything is going wrong, you are being alerted. Or you could do a one-time analysis, as we very often do in order to find bugs in our service. For visualization, as of now, we are using our own dashboards. We write very simple code to graph our solutions. We'll be seeing that very shortly as well. You could go ahead and find tools that work for you for visualization as well. Now, we have used this to solve quite a bunch of real-life problems. Just going to walk you through some of them. First of all was identifying long polls in sub-processes. In one of our cases, we were having our transfers were running very slow. When we were running transfers which spanned several million files, our transfers were super slow, and we did not have an idea why. So when we did this analysis, we realized that there was this method called getFileInfo, which simply did an os.stat operation to get details of file size. And we realized that that's a long poll. Normally, that method would take only 1 millisecond to execute, but it was taking almost 45 minutes. And we realized that the reason for that was that since we were bombarding the disk too much. We were not able, the OS never had time to complete a request and would retry a request while the previous request was still executing. As a result, now this is an OS level issue which we would have never recognized had we not been able to analyze it at such a small level. Another issue which we had was that one of our sub-services was being hammered way more than we intended to. That subsystem did not respond very well, causing in huge delays. We were able to track concurrency of the calling method and realize that instead of having 2,000 concurrent operations, we were having about 120,000. So the moment we were able to fix concurrency there, we no longer had the same issue. There's close the loop measurement, which basically means some of the events which we were starting were never actually ending and were going on forever. Once we realized that there are events who have a start but never have an end, that's a simple cross-join in SQL, then we were able to fix and terminate those events early in case of catastrophe, and thus avoid hammering our sub-services. Now is the time for a little demo that we had. Matthew, could you tell me where the video file for the demo is? Perfect. So just making sure it's playing. Not 100% sure if it's playing. Is there a progress bar somewhere? Perfect, thank you. Awesome. So for this demo, I'm going to assume that you have already written all the you have already generated all the traces you needed to, and you have already shipped the traces to GCS. As I said earlier, there are two methods, cloud logging and GCS, to how to get these logs to BigQuery. For this demo, we are going to do the GCS method. In case you follow the cloud logging method, the recommendation there is to create a sink and simply have the logs turned over to GCS. However, have the logs turned over to BigQuery. However, in this method, we are going to follow the asynchronous approach, look through the GCS bucket, and then import the logs, create a table, and run some queries. So this is what our GCS bucket looks like. As you can see, we have provided a custom prefix for the demo. You can have custom prefixes for each test. If you go into that folder, you will see there is a date-by-date folder so that you can run queries on only the dates you intend to. If you see the full name, it's something like agent name underscore perf log underscore the timestamp. So thus allowing you to provide appropriate regular expressions in order to choose which data you want to run this query on. Now in BigQuery, on the left, you can see there are project queries. Those are the queries that we have already created and saved. We have a set bunch of queries which we use for our experiments, and those queries have been written keeping in mind the kind of tests we run into, but you can obviously go ahead and create your own set of queries. Now, I will be importing a table now. So the way you import a table is to simply go to your data set, create table, and then we are going to choose Google Cloud Storage as source, provide the name of the bucket or subparts of the bucket as a regular expression for which files to choose. So what I'm going to do here is define the name of the bucket in our case and do a start so that we just import everything. We write in JSON. You can choose your own method of writing. Provide a name. Now you can choose schema to be auto-select. However, my recommendation is to provide schema as text so that if there's any changes in the schema, then you can go ahead and catch that at the import time itself. Also, that makes sure that there's no confusion between what is string and what is integer, and BigQuery reads everything as you intended it to. So we have provided the schema here. You can see all those names of the fields. AJ had mentioned earlier about spans. We have flattened all the spans in order to make query analysis easier. Spans would have been like span.jobrun.id, but we have just flattened it to an underscore separated field. We have done a load create job here, so now the load job's happening, and this takes usually a few seconds. Now that the data is done, we can see the data set, we can see all the fields in there. With preview, you can get an idea on what the data looks like in this table. So now we are going to query this table. You can see all the fields in here. Now, for query, I'm just doing a select star with a small limit. As you can see, the query was super fast, and voila, all the fields that you had seen earlier with all the relevant values. Now, let's run a more useful query, something a little more complicated. So I'm going to go back to my project queries and pick one of the queries there to show you in this demo. Yeah, I'm just going to run a concurrency query. This detects how many concurrent events of a certain type are happening. So if you start seeing the query, the first part is just to create a table in which we are filtering out only the events we need from the job we need. Then what we do is we track the start, the absolute beginning start and absolute last end time. We divide the time into intervals of 1 second each. For each of those seconds, we find how many events had started but not yet ended. That way, we know how many events at that point of time were open. Like I said, concurrency, these are a lot of duration events, so we wanted to track start and end. I've hit enter here, so as you can see, this is a really big query, no pun intended, but it is still executing pretty fast. And here we have a result. So if you just go into view results, you can see here that on the left, we have timing in seconds, which is basically the epoch second timestamp, and there's the number of open events corresponding to the same. Now you can choose to export these to a CSV, download, or add to Google Drive, or to a BigQuery table, but I've already done that part here. So now you can see these events in a Google Drive file. I've also downloaded them, and I would be copying and pasting them for analysis. So I created a very minimum bare bones UI. As you can see, it's beautiful. And now we are going to simply paste the events here. And when you plot, you can see what your concurrency looked like. You can obviously automate this entire thing through dashboards. We haven't gotten to automation yet, but in this particular case, for example, we wanted concurrency to be below 2,000, so then we started working on how to lower the concurrency to below that. Yeah, like I said earlier, BigQuery is only limited by our imagination. As creative a query as you write, it is extremely fast to execute. So now is the time for questions.
Thank you, Ankrit and AJ. So is there any question? Edwin?
Can you measure the overhead of this tracing using the tracing itself?
Extremely good question. So for our case, I'll give you the exact statistics with our case. So if we were running, moving big files, say 101 GB files, the overhead was less than 5%, so we could have it running all the time in production, but we never really know what kind of workloads our customers are going to run. If we were running, say, 1 million 1 KB files, which is a very small amount of data, only 1 GB of data. But in that case, we were generating far more events. So in a case like that, we saw about 20 to 25% reduction in performance. And as a result, we don't have it on all the time. We only use it on one-off instances right now in order to track. So based on how many logs you're going to generate or how many events are going to happen under stress, you can decide whether or not to have it turned on all the time or turn it on as and when needed.
Thank you. Other questions? All right. Again, thank you, Alan, Kriti, and AJ.